Okay, hello. Good afternoon, everyone. Welcome to this last pre-training webinar of the sixth training, joint training in atmospheric composition, jointly organized by ECMWF with CAMS, the European Space Agency, and EUMETSAT. My name is Christoph Schröder from the University of Malaga, and I'm your moderator of this last session today. Before introducing the speaker of the session, I would just like to refer to the housekeeping rules that my colleague Michelle has just posted in the webinar chat. Particularly, I would like to highlight that we're going to have now a presentation of 40-45 minutes, followed by 10 to 15 minutes of question and answers. During the talk, you can already post your questions in the Q&A part of the Zoom call, and we will pick them 4 to 5 questions from your the questions to then address them to the speaker. The recording of this webinar will be available for the registered participants and as well as YouTube video of this session. Well, yeah, back to this webinar session. Now we come to the end of this pre-training webinar series and I'm delighted to introduce to you Ed Malina, who will talk today about applications of remote sensing with a specific focus, obviously, on the atmosphere and atmospheric composition. Ed is an atmospheric scientist at ESA, at ESRIN, responsible for the scientific exploitation of ESA missions data for advancing the understanding of the atmosphere. And he has a research background in trace gas retrieval, having previously held positions at both ESA, STEC, and NASA JPL. Without further ado, it's a pleasure to have you, Ed. The floor is yours.
Thank you very much, Christoph, and thank you for inviting me to give this webinar. So you've already heard from previous presentations a bit about remote sensing, some of how we get to it. Now I'm going to talk about how we apply the data we get from remote sensing and how we use it. Now I'm going to, over this seminar, give you I'll give you an overview of some of the capabilities we can do with remote sensing, but then I will focus down a bit more into atmospheric composition areas. I apologize to various of my colleagues and others who I will be not talking so much about in different applications of remote sensing. Their work is equally as valuable, but because of my nature, I have a slant to the atmosphere. So with that being said, let's get going. Now, the first thing I want to make clear is, why do we need satellite remote sensing? This is a scale. So I've chosen an example of the Arctic here. So let's take on the left, our intrepid polar explorer. He or she is a hardy chap who can cover quite a lot of ground in a day, can take a number of point measurements, but they're quite limited in how much data they can provide. So we need to provide even more data over a wider area. So let's go into the middle. Let's use an aircraft instead. So the aircraft is faster, has greater endurance, and can capture more data over a wider area, perhaps take amount of data over 5 hours or 600 kilometers. However, this still quite limits us to quite a small area. And if we really want to understand what's going on the Earth, then we need a much, much greater coverage. So this takes us to satellites. In this case, we've given the issue of the satellite of Cryosat. Now, this is an orbit. It covers the Earth every day. It's been out there for many, many years. It doesn't need to eat. It doesn't need to sleep. It doesn't need to be refueled. And this is really the main way we can get enough data to understand what's going on in the Earth. So now I'm going to give you an overview of the various ESA Earth observation missions we have going up here. This is quite a famous figure that's going out. It covers really well the sort of types of missions that ESA have been promoting in collaboration with our partners. So you'll see 3 streams here. The stream on the left are our science missions, or otherwise known as Earth Explorers. They've been started since the 90s and are currently ongoing. The aim of these missions really is to advance scientific understanding and our ability to characterize unknown processes in the Earth system. And for this reason, they're often very tricky to develop because they're at the forefront of science technology and they need their time, and time is needed to develop this sophisticated science technology to use them appropriately. In the middle, we have our Sentinel missions in collaboration with the European Union under the Copernicus program. So these are more the workhorses of our fleet. They cover a little bit less on the scientific advancement, but more on providing daily high quantities and high quality data to the European and the world communities. And finally, we have the meteorological satellites in collaboration with our partners in the at EUMETSAT. These are long-lasting missions that provide data on climate conditions, for weather prediction, and many other purposes. For the purpose of this talk, I'm mostly going to be focusing on the Copernicus Sentinel missions and our Earth Explorer science missions. So these are some of our Earth Explorer missions to give you a good idea of the range of applications they've been using in. I've circled in red here some of the more key Earth Explorers for atmospheric processes. So the eagle-eyed among you will notice this figure is slightly out of date. So if you see circled on Aeolus, which launched in 2008 and was decommissioned last year. And we also recently launched the EarthCARE mission. Now, these were both very sophisticated satellites looking into wind measurements around the globe, or an EarthCARE will be looking in aerosols and clouds and many other properties. The Fora mission is more focused at understanding thermal emissions from the Earth, and not forgetting our other Earth Explorer missions, such as SMOS looking at freeze and thaw and water, Cryosat more looking at ice, and Flex that's looking at photosynthesis around the Earth. What I'm trying to do here is I'm trying to build up a big picture of how diverse the applications of remote sensing, especially from satellites, can be. Now, moving on to the Sentinels, talk about the current first generation. We have Sentinels here, 1 to 6. Not all of them are up here yet, but these again all provide a wide range of different applications. So the ones that the participants in this seminar will probably be most interested in is Sentinel-5P. This provides global atmospheric air monitoring and greenhouse gases. The follow-on mission, Sentinel-5, is due to be launched in a couple of years and will be providing similar capabilities. Also soon to be launched is Sentinel-4. This is one of our first geostationary satellites that's going to hang over Europe, and the aim of it is to be providing hourly measurements of air pollution, other trace gases over Europe. But of course, we have other applications for different missions. For example, Sentinel-2, which is a hyperspectral imager, can provide data on crop growth or agricultural information, and there are many other applications besides. I also want to highlight here the third-party mission program. So there are a huge number of these days satellites available in space, all with maybe very specific targeted purposes, doing different things. And it seemed important by ESA that we have a relationship with a number of these companies or our sister agencies such as NASA and JAXA to share data. So in order to provide the scientific community and the general citizens around Europe the ability to access some of this data, alongside that data provided by the Sentinels and the Earth Explorers to undertake new science and any other activities. So again, on top, what I'm really trying to emphasize is the huge amount of data out there and the huge amount of applications that could potentially be done with these Earth observation missions. So here is really kind of a summary of what we're trying to do. The ESA missions provides data addressing almost all parameters retrievable by Earth observation satellites, really key parameters about the Earth system. We have provided some idea of the types of things that we can understand from our Earth observation satellites on this particular image here. So for example, greenhouse gases, fire rated of power, sea pollution, snow coverage, air quality, ocean currents, many things we can understand with these satellites. But of course, alas, in the time frame we have here, we can only cover a small amount, and primarily we're going to be looking at those processes related to the atmosphere. So another important aspect I really want to get across to you all is how we deal with data. So we've talked about remote sensing data, but what does remote sensing data mean exactly? So the data I'm going to be talking about in this particular seminar is more what we call level 2, level 3, and level 4. Level 0 and level 1 is data what you get is more what you receive from the satellite itself. This is then beamed down to the Earth and more processing is performed on it. So at level 2 is where we convert this raw satellite data into specific geophysical variables. In this case, it's the TCI concentration, or this could be a methane concentration or a carbon dioxide concentration. From level 2, we go to level 3, where we can aggregate these individual points into ideas about methane over, say, France, or a specific city in France, say Paris. And level 4 is when we take additional information and start to understand a little bit about flux rate, say the rate of methane or CO2 change in say Paris. Now again, what we're mostly talking about in the application of remote sensors are these data levels 2, 3, and 4. So now I want to give you a little bit of a talk about the heritage. Where have we come from? Excuse me. So if you remember, if you cast your mind back to when I showed you the 3 streams of ESA missions, at the very beginning of the Earth Explorers, you will have seen ERS-2. Now on ERS-2, there was the Global Ozone Monitoring Experiment, otherwise known as GOEM. Now this is one of ESA's first missions towards measuring a number of trace gases, such as ozone, or in this case shown here, nitrogen dioxide. Now, the particular point I want to highlight here is the spatial resolution. So what this means is the coverage it could see on the ground. And the spatial resolution it could see was 40 by 320 kilometers, which are really, truly enormous footprints. You can see examples of this on the maps shown on this image. And this is particularly highlighted on the image on the right here. So this is an image of NO2 from GOEM over the Italian peninsula. So you can just about vaguely see there's more NO2 over northern Italy, say Milan in the Po Valley, and a little bit more about, say, Rome. But this is about the amount of information you could get from satellite launch from 1995. Fast forward a few years and we get to the instrument ECMWF on ENVISAT, which launched in 2002. Now here you can see we have smaller footprints. If you look at this slightly figure, the footprint's a little bit smaller, of 96 kilometers by 32 kilometers. And this has, again, for NO2, allowed us to resolve a little bit more information about where, say, NO2 is coming from. You can see here from this map from the University of Bremen that we're able to highlight North Sea oil rigs emissions. We also had cities such as London and Birmingham and Vienna. So again, this is an advance of capabilities moving from GOEM to ECMWF, and in the future I'll be talking about what we are capable of doing now. Now moving on to a different gas and a different satellite launched in 2009. This is an ESA satellite. This is GOSAT, I've mentioned before. I like to talk about GOSAT. I studied GOSAT for my PhD, and GOSAT is particularly close to my heart. Now, GOSAT was the primary workhorse for measuring methane and carbon dioxide for many years. It was launched in 2009, and the reason I call this heritage-ish is because it's still up there providing measurements and providing science. Now, you'll notice from the figure on the bottom right here is the interesting sampling pattern undertaken. You have it takes pinpoint measurements and then moves along track here, bang here, bang here, bang here, and then moves along. Now, the distances between these particular measurements can be quite large, which means it's very difficult to understand pinpoint sources or specific locations due to the distance between these measurements. The best that really could be done with GOSAT is take trends over large areas. For example, we have a look on the bottom left. We have methane trends from different particular emission sources, say oil and gas, or from wetlands, or from livestock, over effectively the entirety of the United States over a number of years. While this was still really relevant new information provided by GOSAT, it's still not quite enough to help us truly understand where a lot of greenhouse gases or other trace gases are coming from in the atmosphere. And this is information that we really need to understand. So then now we come to where are we at now? How are we resolving this? So here we come to Sentinel-5P TRPOME. So TRPOME was launched in 2017 as a collaboration between the Dutch government and ESA. It's capable of taking measurements of a wide range of gases, such as ozone and methane and water vapor. And the particular point I want to give to you here is it takes measurements with a footprint of 5 by 7 kilometers, depending on the band, which is far in advance of the instruments I've been talking to you about before. Now you can see on the figure on the bottom left here is one of the first published images of nitrogen dioxide from TRPOME, and you can instantly see much finer resolution on NO2 emissions over Europe. You can even see, quite famously, if you see here, these ship tracks going from the North Sea down by Spain and through the Mediterranean. So now at ESA, typically when we design a mission, we have a number of targeted trace gases that we go for. So Sentinel-5P in particular was targeting ozone profiles, aerosols, methane, sulfur dioxide, formaldehyde, and many other trace gases. We target that these are all decided early and each of these are particularly important in the Earth system for one reason or another. For example, I focus particularly on NO2 so far because it's an atmospheric pollutant, and it can be detrimental to health, and if it's breathed in, and therefore it's particularly important for us to understand where nitrogen dioxide is and how we can map it and where it's coming from. So now we will move on to a little bit more about the exploitation of these products that come from these instruments. So let's first have a look at ozone. Now, it was found out back in the 80s that our use of appliances was emitting certain ozone depleting substances that caused a hole in the ozone layer. Now, this led to the Kyoto Protocol, which banned these substances. And ever since then, we've been monitoring the recovery of the ozone hole since then. Now, in this case, what this image is showing is the decrease of the size over the ozone hole over a number of years, over the key months, how with ozone chemistry changing the size over these months from the summer to the winter. Now, this isn't strictly speaking just data from TRPOME. What's happened here is that the CAM system that has been talked about in previous lectures is assimilating data from Sentinel-5P in order to provide better estimates. And this has allowed us to estimate a bit better the ozone hole recovery. Another example of, again, here we cover this a lot, NO2, tropospheric column pollution. So what we're looking at here is two particular images, an average of NO2 data from March and April in 2019 and the difference between that and NO2 pollution data from March and April in 2020. Now, as I'm sure all of you remember, in this period, we had the COVID lockdown, which is well known to lead to dramatic reductions in NO2 pollution. Now, this is something can be clearly seen from this image from one year to the next, with key NO2 emitting cities such as highlighted here, Paris, Barcelona, Madrid, Milan, and Rome, dropping dramatically in the amount of NO2 concentration over this period. And this is another example of how data from S5P has been helping us understand air pollution. Now, another particular air pollutant we should be concerned about is sulfur dioxide. Now, sulfur dioxide is emitted as a part of industrial byproducts, but also in this case, it comes from volcanoes. Now, what we're looking at here is SO2 emitted from a Russian volcano, Shivluch. I'm not entirely sure if I'm pronouncing that right. Apologies if I've butchered that. But what we're looking at is the emission of SO2 and its transport over a number of days and how it's been tracked using S5P. Now, pollution transport is a particular issue that we all need to be aware of. As we can see here, that the emission of SO2 from the volcano in Russia ended up in the United States just a few days later. Now, this isn't just SO2. We have to consider it's about all trace gases, depending on their lifetime in the atmosphere, get transported around by winds or by other means that may mean that your emission in your local environment may well impact somewhere else on the Earth. Another key issue that has arisen, especially in the context of climate change, is emissions related to bushfires or wildfires. So we've chosen this particular example here of wildfires on the east coast of Australia in late 2019 and 2020, but this doesn't have to be the case of only Australia. We've seen wildfires in California, in many other places around the world. So what we're seeing here on the left is the emission of carbon monoxide, another pollutant gas from these fires and how they're transported over the particular ocean. Now, a particular challenge from carbon dioxide is, from Sentinel-5P is that S5P can't measure carbon dioxide directly, but what we can do is measure carbon monoxide. And from the carbon monoxide, we've been able to estimate the amount of CO2. And from that, using these satellites, we estimated that in 3 months, the Australian bushfires emitted nearly 750 million tons of carbon dioxide. Now, if you consider that is just a few months in 1 year from wildfires, and this will be scaled up depending on across wildfires across the world over a number of years, it has quite a significant impact. There was another study that's linked below of how the emission of aerosols from this particular wildfire also led to huge growth of algae plumes in the Pacific Ocean, not too far away, which was also detected by remote sensing applications. Yes, up here, there's a link to it here if you are so interested in learning more. So these products were already anticipated and designed to be included as part of Sentinel-5P. But another significant part of what we do at ESA is we're looking for innovative ways of exploiting data that's available from these satellites that haven't been thought about before. So over recent years, we've been looking at investigating ways of measuring additional trace gases from these satellites. For example, we've been looking at Glyaxal for tracing tropospheric ozone. So ozone's important because ozone in the stratosphere, it protects us from the UV radiation, but ozone in the troposphere acts as a greenhouse gas and a pollutant. And it's important for us to understand where that is and where it's coming from. Other new data products we've been looking to provide information about includes chlorine dioxide, which destroys ozone in the stratosphere. Again, we need ozone in the stratosphere to protect us from UV radiation. And there's many other interesting applications, such as solar-induced fluorescence, which can give us an indication of global vegetation health, or ocean color, which can give us some information about the health and content of the ocean. So, if I may now, I'm going to move a little bit away from Sentinel-5P. There's some other applications of remote sensing that have come up recently. Here, I'm showing examples of high spatial resolution satellites, such as this mission Prisma or Sentinel-2, with spatial footprints of 30 meters or 20-30 meters, showing the ability to pinpoint methane sources from oil rigs or from petrol generators in well-known regions. This is quite new research and quite exciting, and may well help us lead us to pinpointing really high methane sources from these emitters in the future. So, particular what came out of this is banding a number of these satellites together. For example, on the left we have Sentinel-5P, which was able to detect that a plume existed, and then we zoomed in on using Sentinel-2 to pinpoint the exact location of the plume, and then with Sentinel-3 we were able to see how long the plume lasted for. So this is a particularly important point to cover in the future, is how we cannot just consider individual satellites by themselves. We have to consider how we can use all these satellites together. So this comes to multi-instrument synergy. For example, here's another application of using multiple instruments such as Tropomi, OMI, and other ones such as EUMETSAT's EASI or the Korean GEMS to try and understand nitrous acid, which is, while less important for us to understand it exactly, it's important to understand it's a source of hydroxyl radicals, which are a sink in the atmosphere of methane. So the presence of hydroxyl in the atmosphere is fundamental in our ability to scrub methane from the atmosphere. So going from usage of data from a specific level, let's go to how can we exploit it to another degree. So this is more thinking about the level 4 data I've been talking about. So I'm going to highlight a particular project here called CitySat Air, where we've been combining Tropomi measurements of NO2 in combination with in situ measurements from city networks, such as or individual sensors in a city, to try and understand at a fine scale and predict urban air quality. Now, the methodology for this particular process is shown on the right. I'm not going to go through details on it. If you are interested, you can look at it later on. But the key point is we're combining all this data to be able to downscale Sentinel-5B data to be able to really see where the nitrogen dioxide pollutions are in a city. You can see this online, this CitySat Air project. It's you can predict and have a look at the air quality in a specific region. So in this case, we're looking at Madrid. And you can move your cursor around and see what the NO2 is at a particular time. Another example is Alpine Air EO, where we're looking over the Alps this time. And in this case, this particular project was aggregating satellite measurements from a number of different trace gases and model measurements, including NO2 or ozone or particulate matter, in order to form estimates of what is called the aggregate risk index. So a quantitative description of the health risk, your health risk due to short-term exposure to air pollution. And you can see here it's very clear, quite clear over the Alps itself, but then quite bad over Milan. So I've talked a lot about the Sentinels, but let's have a quick look at the Earth Explorers, as they are quite different and less about trace gases. So I pinpointed Aeolus earlier. Now, Aeolus was the first wind LiDAR measurement in space, and it was quite an exciting mission and very sophisticated and advanced. And it's helped us understand global wind movements and help. And the data from Aeolus was integrated into ECMWF models to help better predict future weather using numerical weather prediction models and help us understand climate science better. It also helped to gauge velocities from hurricanes and help us better understand these big global circulations of air that go around the world. So, but also an interesting aspect that came out of the measurements, again, is outside of what was initially proposed for Aeolus, is the ability to provide new data and new science. Here, for example, there are a number of projects ran out of what's called Aeolus Plus Innovation, where the LiDAR measurements were used to generate a new series of information, such as top one called LISA, which was LiDAR measurements to identify streamers, i.e. lightning, and analyze atmospheric waves. Data from Aeolus has also been able to use to improve dust aerosol forecasts or derive ocean surface wind products, or study whether in-water products can be retrieved from Aeolus. So the key point I want to highlight to you all is that the satellite mission is up there, it has a number of products, but that is not the be all of the end all. There's always something more you could do with it. You can always improve the products, you can generate new products, you can generate new science, you can do new things. And moving, particularly important point coming on is now EarthCARE. Now, EarthCARE launched very recently. It has a number of different instruments, and it's going to be used for profiling clouds and aerosols, optical depth, and understanding radiation emission from the atmosphere. The data is going to be coming out over this year, and we're still looking for new and innovative ways to use the data coming from EarthCARE. And this is quite an exciting prospect of what might come out of EarthCARE and how we can benefit global citizens using this data. Now, again, I want to emphasize synergies between different satellites. So it's potentially come apparent from the various points I made through this presentation is that each satellite is capable of a certain thing, but it may have certain weaknesses and some limitations. So how can we potentially come over those is by using measurements from multiple satellites and using their strengths to overcome limitations in across other different satellites. So in this case, we are looking at a project called AirSense, which is bringing a number of different instruments together to better characterize aerosol spectral properties or aerosols in general. Aerosols are quite important because they have an impact on the climate. They can have an impact on our measurements of radiation from the atmosphere. And they can also have an impact on our health, which is why we're particularly keen on understanding the distribution and types of aerosols that go around the globe. Another key point that we need to bring out is that while we can take these measurements, what we really need is long-term data sets. And by combining measurements from a lot of different satellites, we can form these long-term data sets in order to better understand how aerosols or any other product really changes over time, and maybe we could be able to use that information to predict changes. So now I'm coming towards the end of my presentation. So what we need to talk about is, well, what's coming next? So I've talked a lot about Sentinel missions. So you can see here on the left, we have Sentinels 1, 2, 3, 4, 5, and 6. These have all different instruments on it to do different things. So we have new versions of these coming out soon. So for example, Sentinel-1C was launched recently. And Sentinel-5 should hopefully be launching next year, and Sentinel-4 soon. So these will be continuations of the current satellites as they age and degrade, to ensure that we have constant information coming out from our satellites, ensure there's no gap, and form these long-term data sets that I was talking about. We also have what we call the next generation of Sentinels, so forming from lessons learnt from the current generations of Sentinels. So we have Sentinel-1 NG, Sentinel-2 NG, Sentinel-3 and different types. Now, I particularly want to highlight Sentinel-2 NG. Now, I pointed out earlier about finding methane emissions at high resolution using Sentinel-2. Now, this was never anticipated during the design and operation of Sentinel-2, and it's a very recent aspect. And in response to that, there has been some thoughts or talk about, could we design Sentinel-2 NG, to be able to take advantage of this capability that we didn't know it had. So this is another example of how science and exploitation of remote sensing data can help influence upcoming and new Sentinel missions. So also we have the Copernicus expansion dataset. So we have these range here. So that's ROSE-L, CO2M, Crystal, CHIME, LSTM, and SIMMER. Now, from what you'll see from all of these, they're all targeting very different things. So ROSE-L is radar using L-band SAR, targeting the Arctic to understand the cryosphere, how it's degrading, how it's changing, and so on, and different things. CO2M is an exciting one, especially for this audience, as it's building on the heritage of the Sentinel-5 and Sentinel-5P missions, and it's primarily going to be focused at carbon dioxide monitoring, but also methane, but at a much higher spatial resolution and at higher accuracies and currently capable from Sentinel-5 or from the Sentinel-2 missions. And the spatial resolutions I talk about here are, say, 2 by 2 kilometers. Again, we have CHIME. Now, CHIME is another interesting high spectral imager, similar to Sentinel-2. Again, is CHIME a potential option for pinpointing methane sources or for other sources? It's not designed for it at this moment, but it may be capable of it, and this is something we should investigate and find out in the future. So here is a nice image of these individual satellites that pinpoints really what their applications are. So you can see for CO2, it's looking to focus on climate change. Sorry, CO2M is looking to focus on climate change, primarily from human activity. We have LSTM to understand water resource management and droughts. We have CHIME that's looking in a similar area for food security, so soil properties and crop health. And then we have going towards, again, land monitoring and natural resources with Roselle and Simmer, looking at from Roselle the cryospheric region and food security, Simmer looking at sea ice concentrations and the cryosphere. Now finally to Crystal, which is focusing specifically on the Arctic, that's going to be looking at ice sheets and glaciers and snow. What should be very clear to you all here is the really diverse range of applications that each of these satellites have, targeting many different aspects of the Earth system, and particularly how that impacts the average European or global citizen. Now, also, if you remember casting back to Earth Explorers, I again apologize to colleagues for only focusing on this particular Earth Explorer forum. There are a number of others going up that are also equally worthy of mentioning, but in this case, we're focusing on forum that has the nice, snappy tagline of understanding how the Earth is losing its cool. So forum is going to be looking at the very, very far thermal infrared, an area of the electromagnetic spectrum that we have not studied yet, and we just don't know how what impact that spectral region has on the atmosphere, or what emissions from the Earth, what impact they have. And this is why this is placed in the Earth Explorer program. This will be new science, new knowledge that will generally be provided. And alongside this general information on the fire and from air, there's potential to be able to understand other aspects of the Earth system, such as tropospheric and stratospheric water vapor, potentially CO2, and understand a little bit the impact and changing of ice clouds. Another important aspect of what's coming up, and it will be using Earth observation, is the Digital Twin Earth program. Now, what we're attempting to do is we're trying to develop a system that can, an interactive system that can replicate aspects of the Earth system. Now, this will be using a combination of different information from models, from in situ data, from citizen science, from Earth observation data, and we'll collate this all together over time to be able to downscale and reconstruct specific aspects of the Earth system. For example, maybe we can reconstruct the Arctic using all these data in order to be able to predict glacier shift, ice flows, melt and thaw. Or we could look at air quality. We could you can use all the data to develop and understand in the future, perhaps on a certain day, given these conditions, what air quality might be in June over Vienna. This is currently the future of where Earth observation is going, and it's quite an exciting opportunity that will be coming up. Other aspects include a nice interesting development called high altitude pseudo satellites, or HAPS. So while satellites can provide a lot of information very quickly, what's often missing from satellites is persistence at very high spatial resolution. So we need to understand hour by hour, minute by minute in some cases, how, say, changes occur over a certain crop. Or perhaps you need to understand sea level changes in order to understand if a dike in the Netherlands is going to crack. This is where these HAPS may come in. These are specific aircraft or balloons that can hang over a certain area for days, months, or even years in order to provide long-term measurements over very specific points. Now, this is a particularly challenging technology, especially the aircraft, which require a number of solar panels in order to stay up for a long time, and may well not work so well in higher latitudes where there's just not enough solar energy, and therefore the aircraft will not be able to stay up. So this is the end of my presentation. I'm hoping that I've given you really quite a wide-ranging view of how remote sensing is applied globally and the different types of topics it's used for. And I'm very happy to take some questions now.
Yeah, thank you very much. I had a really nice journey from the past to the present and future of remote sensing and this is satellite Earth observation. I don't see any questions so far in the Q&A. Just maybe a short question from my side. I don't know whether short, but so I mean, you've presented or mentioned this increasing combined use of satellites, banding together satellites, multi-instrument synergy, also downscaling of existing data, versus, I don't know whether versus, but and in combination with the new generation and Copernicus expansion missions. Where do you see where would you see priorities in if you would need to set priorities in using or an increased use of the existing ones and combining combined use and finding the synergies between what is there, or are there still very gaps that you see which require this new generation and expansion missions?
I see both, in honesty. I've tried to highlight throughout that the spatial resolution on satellites is sometimes not sufficient. And as our technology improves, that means we generate new and higher spatial resolution satellites, and we still need this. So while the combinations of satellites do give us a lot more information, they sometimes cannot. There's only so much that one can do. So particularly in pinpointing a very specific source. So the answer to your question here is that we need both, and we need, with all things, and to try and maximize as much information as we can with as many measurements as we can.
Great, thank you. Thank you very much for this. Are there any further questions from the audience? I don't see any. If someone like to raise his or her hand. Well, I think the participants are overwhelmed by this wealth of information. I think there's a lot of to digest and to see the application applicability of what is there and what will come up.
Well, for those of you,
sorry.
For those of you coming on the course, I'll be very happy to take questions there.
Exactly. I think I just wanted to mention that possibly with some time to digest the information and in place, there are going to be some further discussion and discussion with you. So if there's any further question, then I really would like to thank you again for this presentation, for the insightful presentation, also to the participants for the interest, and would like to close the series of retraining webinars that we have had over the past 3 days. I wish you, all the participants who will be in situ in Norway next week, best for this in-person training, and thank everyone else for the participation.